The next speaker in this session is Sangjun Jeon from Chung-Ang University, Engineering and Observation of Majorana Zero Modes.
Okay, thanks for the introduction. And personally, it is a great honor to be here as a member of Korean team and have a chance to explain my experimental works in front of distinguished professors from Korea and Israel. And it is a great pleasure to be here, the historic place in Jerusalem. And actually, yesterday's tour of Old City was very exciting to me, and see how people with different ideas and different thoughts were living together in a city. It was very impressive to me. Mm-hmm. Okay, back to scientific talk. The title of my talk is Engineering and Observation of Majorana Zero Mode. And actually, Majorana Zero Mode is interface state that just the question is raised, right? So two different topological modes, and at the interface, you can get a zero mode. And what I'm talking today is basically experimental observation of this kind of things. The talk is basically the summary of what I've done when I'm doing a postdoc in Princeton University with Professor Ali Yazani. It's been great works, and then I think it's a good example to show how experimentalists work together and merge the ideas from theoretical proposals, and then try to get some evidences of how to realize the idea and then support the ideas. And sometimes this new observation can refine the theoretical works. So I think this is a good time to share my works. Okay. Since I'm moved to Chung-Ang University, so I briefly introduce my university too. So Chung-Ang University is located in Seoul, the capital city, and actually it's located almost at the center part of the Seoul. And Chung-Ang also means the center, so you can remember this is Central University in Korea, in Seoul. And I also built my own lab in Chung-Ang University, and this is my low temperature system, and especially this one is designed for studying two-dimensional systems. So later on, I have chance, then I could share my new data out of this one. But today I'm going to focus on Majorana. So I think most of people know what is Majorana, but I briefly introduce what is the Majorana terms come from. So actually, the term Majorana is coming from Majorana, and the history is come back to Dirac equations. So Dirac tried to make some first-order wave equations that matches Klein-Gordon equations, and then he found that this alpha and beta has to satisfy anti-commutation relations, and for that, so he realized that the wave function has to have complex numbers with 4 elements in it, and then he predicted the particle and anti-particle and spin in there. And later, Majorana found another solution that matches Dirac equation to the Klein-Gordon equation, such that by using these parameters, he can find that the Dirac equation is solely made of real numbers, and the wave function is also real numbers. So as a result, mathematically, I can predict a particle that is its own anti-particle, and people follow his name, and then this is the history of Majorana fermions. Okay, in condensed matter, what we are doing is there are lots of quasi-particles in there, and people try to looking for a particle, quasi-particle that behaves like a Majorana fermion. And probably the good starting point is the superconductor, because the superconductor has particle-hole symmetry. In condensed matter, we know, so electron quasi-particles, and the counterpart is whole quasi-particle that behaves like an anti-particle. So if you consider the relationship between particle and anti-particle suggested by Majorana, so we can consider the particle and electron and hole parts in superconductor. And especially once you get some in gap states, it always show up in pair because of this particle-hole symmetry. And especially you tune the energy as zero energy, then maybe you can say, oh, this wave function is particle and antiparticle at the same time. And one way to generate this kind of in-gap states within the superconductor is using magnetic atoms. Once you put magnetic atom, magnetic moment, surrounded by the superconductor, then you can see this kind of bound states. And one located at minus energy, and the other is located at energy always because of the particle-hole symmetry in superconductor. And we call it, there is a U, Shiba, and Luzhinov state. And then, of course, the energy can be tuned by the coupling strengths between magnetic atoms and the superconductors. So in principle, we can get a zero energy in this state. But this is maybe interesting, but it's not useful in practice because if you apply some kind of small perturbation nearby it, then you can, the energy, zero energy state will shift out of it, and it is not Majorana-like particle anymore. So here comes the idea from Kitaevs, and he suggests that if we are able to get one-dimensional and spinless P-wave superconductor in condensed matter system, and with his toy model, there is a ground state that has two Majorana modes localized at the end of this chain. It's basically very similar idea as Zak Phase. I'm sorry. So it is, the reason for that is you can consider this is topologically non-trivial part, and then the other side is topologically trivial part, different Zak Phase, so you can get this one. It's also another way to explain it. And the interesting part of this model is that, so even the states are protected. So if you have some other perturbation, potential perturbation or whatever is located nearby it, it will not move these Majorana states out of the zero energy and shift from these locations. And moreover, and he proposed, Kitaev proposed that by exchange the position of these two Majorana modes, the wave function can get some finite phase. And then he thought that by using this functionality, so we think we can make a content computations out of it. So that's the very strong motivation that people working on this project. Okay, so this is some background. And then as an experimentalist, and then how we engineer and how we realize this Majorana zero mode is following. So starting with P-wave superconductor will be the easiest way, but as we know, there is no, P-wave superconductor is very rare in nature. So starting point is normal, conventional superconductor. And we try to induce the superconductivity to non-trivial nanosystems. For example, this system, it could be a one-dimensional system or two-dimensional system. And then the number of crossings at the Fermi level has to be odd numbers. Otherwise, it will be, again, the trivial phase again. So to get non-trivial phase of it, so we have this condition. And at the same time, if you want to open a gap, I will show you later, then the spin of the space has to have a non-orthogonal components in it. So okay, this is some ideas we got from the theoretical proposers. And then to get into real materials, we have to consider these things. The first thing is strong Rashiba spin-orbit coupling. So we know that if you have spin-orbit coupling in the momentum space, the spin degeneracy is decoupled in momentum space. And the other thing is using Zeeman splitting, basically the external field and the exchange coupling, then energetically the degeneracy is shifted. So by doing this, in principle, we are able to get some spinless systems. And the other thing is using topological system, either in 2D or 3D-dimensional system. There is very strong spin-orbit coupling in there, so it is effectively, you can make a spinless system and induce the superconductivity at the Fermi level, may get some signature of this Majorana-like quasi-particles in condensed matter systems. Okay, of course, we have to consider when we designing or engineering the system, we have also consider the dimension and how we able to terminate the system. Otherwise, everything is in same phase, same topological phase. We cannot see these bound states. So that is also important part. So there are a couple of, actually more than several proposals to realize this kind of Majorana zero mode is following. The most well-studied system is semiconducting nanowire system, where the strong spin-orbit coupling in the nanowire closely proximatized to the superconductor, and by applying proper magnetic field and tuning, then you can get zero bound state at the end of this system. And the other thing is they're using magnetic atoms on a superconductor, and then and the other thing is the topological system with a superconductor, three-dimensional topological system, or two-dimensional version of the topological system. And today I'm going to mainly focus on these two systems. Using scanning tunneling microscope, we engineer and combine the materials to get these geometric structures and then measure the electronic structure using scanning tunneling microscope. And that's the, basically what I'm going to talk about today. Okay, the first part. So we know that from the U-Shiva region of state, once we put single atom on a superconductor, there should be a bound state inside a superconducting gap. This is the localized, very localized nearby here. But once we make a chain out of this magnetic chain, magnetic atoms, and then this localized state will have some dispersions like this. Okay, so within the superconductor, the states will make some continuous distributions in momentum spaces, and especially the bandwidth is small enough such that there's no crossing point in between these two. Actually, this is the particle hole symmetry coming from the superconductivity. Then you may expect that there is no state at the Fermi level, and this could be another gap. But as you see here, this gap is topologically triggered. There's nothing changed compared to a normal superconducting gap. But once we have this kind of crossover, so negative mass, you can say negative mass, or band gap inversion in the same way as the topological insulator, then there should be some number of crossing points. And especially if the crossing point is odd number, then and if there is some gap opening due to the spin-orbit coupling or some other non-parallel spin components, then you can get topologically non-trivial phases in these systems. That was the basic idea we had. And there's another proposal such that, so if this is really a parallel configuration, the spin components, then there's no way to open a gap at the crossing point, which I just showed here. So for that, the people expected to have some helical, non-collinear spin state of the magnetism can give us Majorana-like zero mode. This was the very early stage of proposals. And then by keeping in mind all these theoretical proposals and our understandings, we choose a material with lead substrate on a ion chains, and then we measure with the scanning tunneling microscope. So scanning tunneling microscope is basically we measure the tunneling current between tip and sample, and by moving the tip positions on the surface, we know where we are measuring, we know the structure, and at the same time we measure the dense state, which give us electronic properties of the sample. So there is very powerful measure this kind of localized states. And especially we use the spin polarized STM to further characterize the system. So this is functionalized with some magnetic atoms. So the tunneling current has some spin component, spin dependent tunneling happens. So we can characterize what's really happening in this localized state. That was the our measurement setup. Okay. As I mentioned, so we choose lead substrate, which is a single element superconductor with very relatively high critical temperature. And then we choose iron as magnetic atoms. Actually, at the beginning, we tried to manipulate a single atom to make a chain structures, but it turns out very hard to manipulate on lead substrates somehow. And then we decided to use some self-assembled method to get wire structures. So basically, you evaporate the atom, and using some heat treatment, then you will find some minimum energies, and then it is making some wire structures on a red substrate. So we have all kind of ingredient in there. We have a very strong superconductivity, and we have the magnetic chain, one-dimensional magnetic chain on there, and probably we have some kind of strong spin-orbit coupling inherently from the lead elements. So right after we got these kind of structures, we directly measure this, the spectroscopic signatures of the zero energy state, and then it turns out that it's very robustly we can find the localized zero energy state. So this is topograph. So as I mentioned, scanning tunneling microscope tells you the structure of the system. This is the one atomic width of the atomic chain made of iron, and then this is the upper part and the lower part. Actually, in between there is some unknown structures. It's hard to understand it, but at least there are two clean parts. Is elongated in. The length scale is about 5 nanometers to 20 nanometers or so. So it is very relatively long nanowires. Okay, so and we move the T position in every different positions, and especially at the end, only at the end of the this chain, we are able to get this zero energy state in tensile state measurement. So this is a better way to display what's really going on. So this is the distance. Basically, you move the tip from here towards the inner side of the this atomic chain. So if it is outside, you see this is the superconducting gap. And if you go inside, then there should be the Yeshiva region of states or a band of the Yeshiva region of states. This is the band of singularity of that bands. And as you see here, at zero energy and located at only at the end, the zero energy state is just show up here without connecting to other states. And similar thing happens in here. And then we saw that, oh, this could be something special, but it could be other trivial states because it is end. End is always special, so we have to find more evidence or support our ideas. So next thing is try to see what's the magnetization of this nanowire system. So as I showed you in theoretical proposals, so we wanted to see helical states of the magnetisms. So using scanning tunneling microscope, we try to look at some changing of magnetization in structure along the wire. But as we measure here many wires, many chains, it turns out that it is ferromagnetic systems. So it was very confused at the moment. How can you get some zero end state with a ferromagnetic chain on a superconductor? And so we do more and more measurements on system, and fortunately we got some interesting data on red substrate, and red is in the magnetic system. So even though using spin polarized state, we don't expect any magnetic signals out of the red substrate, but somehow if you change the magnetic field, there is related, there is some, you see the tunneling current is changing as a function of magnetization. So it is a bit tricky to understand what it is on, but we think this is really related to spin-orbit coupling of the red substrate. And that couples the magnetization of this magnetic ferromagnetic chain that can open a gap. So this is some kind of refinement of theoretical proposals in our understandings. And still, there are criticisms that how can you? So what we collected so far is the experimental evidence, but is some kind of supporting evidences. But what is really actual direct evidence of the Majorana zero modes to get to understand this picture? So we use spin polarized STM measurements, and as you see here, so in our understanding, zero energy state doesn't have the spin polarization because it is cancelled out by the background. That is our understanding. But somehow, if you use the spin polarized STM by flipping the spin up and down, measure the same wire, exactly the same wire, and you see the end state, zero energy end state has some strong spin polarization. This is very unexpected results, and then we think this is can be understood as something related to topological non-trivial character of these zero end states. Okay, this is one successful story, what I showed you, but actually this was one successful story, but there are lots of failures in there. So for example, why we choose iron and why we choose red and why we choose this kind of structure is all as of after the many failures we get to these results. So this is how experimentally is to do the work normal days. And the other thing is the quantum spinor system with a superconductor system. So we tried to get other one-dimensional system, and then this is a good example. But again, the quantum spinor system is very special, and it's hard to get in normal natures. But interestingly, we got very good. We have lucky, so we found some spin hole systems in very unusual way. So let's explain what's really going on in this system. So let's assume that this is a quantum spinor system or two-dimensional topological insulator system. And then you will get a boundary states. And this is a helical boundary states, very strong spinor coupling. One is going around here and the other is going around this way. So this is one-dimensional and spinless system as the K-type mentioned. And then we wanted to induce the superconductivity on this kind of electronic states. Of course, by doing this, this is all topologically non-trivial state is going around this two-dimensional system. So we need proper termination to get the zero end state. So this is how we actually put some magnetism to get topologically trivial gap. And then this is topologically non-trivial side. So you can expect to see the interface state at the interface here. That is our original idea to get to realize the Majorana zero modes in here. So the elements we choose is here is niobium and bismuth and iron again. So iron acts as a magnetic cluster to get a topologically trivial gap, and then niobium acts as a superconductor to induce the superconductivity to the non-trivial system. And actually, the key part is the bismuth. So the reason why we choose the bismuth is we have to go back to many years from here. This actually we published it in 2014. So at the moment, we found that we tried to understand the bismuth because bismuth is one of the first system that behaves quantum spinor system when it is in single bilayer system. But we cleave the bulk bilayer system and measure the surface states and edge states. For example, here, this is all edges of the bismuth, and we also measure the surface states here. And then we found very strange electron states of all surface states and edge state. Mainly they are coming from the strong spin-orbit coupling. And especially if you measure the interference pattern along the edge of the bismuth, we found that there are very nice interference pattern. And by Fourier transforming it, we can understand the dispersion of electron states lying localized at the end of the step edges. And then by analyzing the data, we found that there is no backscattering in there. That means there should be a spin up component and spin down component, but they are living in a different states, so they do not interact with each other. In other words, this could be a signature of helical edge states living in one-dimensional states. So we knew that this one, and at the moment, yeah. This one, no. At the moment, this is the just bulk bismuth, so there's no gap in there. Okay, yeah. Maybe I know there is some problems in there, but okay, I'm gonna continue. One interesting part is that we found two different kind of edges. One is we call it A edges and B edges, and somehow only one side of the edge give us this kind of localized helical edge states in there. So at the moment, we didn't know much about it, so we thought that this is some kind of hybridization issues. One side is strongly hybridized to the bulk system, and the other is not the case. But later, people had more ideas about the system, and then introduced the high-order topological insulator, and then it looks like the bismuth is the one candidate of having a hinge state from the high-order insulator. The name changes from the quantum spinor system or the high order. It doesn't matter. The system, the edge state, has a helical one-dimensional system. That was the interesting part, experimentally proven fact. So we decided to induce the superconductivity to these bismuth systems. So we used the niobium as a substrate, and we make a thin film of bismuth on it. So actually we use 4 to 5 layers of bismuth. The reason for that is if it is too thin, then it will not grow in one directions. So it will not give us this kind of special edge states. If it is too tall, then it will not get strong enough superconductivity from the niobium. So in our experience, 4 to 5 give us good systems to understand the Majorana states. So of course, we have to check whether how many states are there at the Fermi level where we wanted to get some topological non-trivial states. So this is basically we measure the density of state as a function of position along the edges, which we did before on a bulk state, and this is thin film state, and then we found that only one state is actually pass through the Fermi energy that is related to odd crossing numbers of the surface states, edge states. And later, here actually we turn on the magnetic field to suppress the superconductivity of the niobium. But once we have zero magnetic field, you will get a superconducting gap, which is actually proximatized, induce the superconductivity on a bismuth surface and bismuth edge states. So here is the location of the edge, and then you see the gap size is different. So one side, this one is the red one is the superconductivity at the surface side, and then the blue one is superconductivity induced in the edge states. There are some difference in there. So we successfully induced the superconductivity to the system with one-dimensional helical state. That was the in our understanding here. And the next thing is we wanted to terminate this helical edge states, superconductivity. So this is some kind island of made of bismuth films, and then we evaporate iron again, and then interestingly, iron is decorating only the B edge side, which is very strongly hybridized or topologically the hinge state is not existing in here. So this is a good one-dimensional state here, located here, very well localized. And then we induce the superconductivity on here, and it's very well terminated in both ends. And then we measure the spectrum here. This is the edge state. And as you see here, as you go over through these magnetic clusters, and you see the zero end state is located only at the interface here. And the down part is again the same here. So you see the zero end state is located at the interface here. So this is how we understand the theoretical proposals and to realize in real materials. So maybe it's too early, but I'm going to summarize here. So basically, here I introduced 2 ways to generate Majorana zero modes in condensed matter system. One is using a magnetic chain in one-dimensional form and induce the superconductivity, and the other is using helical edge state and induce the superconductivity and terminate properly with topologically trivial gap to get Majorana states. So basically, what I want to tell you today is this is maybe it's not the most updated story, because the last paper was appeared 2019, something like this. So it's 2 or 3 years ago. But I think it still how we develop the ideas and then collect the materials to get the right spectroscopic data. It was very interesting in my experience, and I want to share my experience to all of you guys. Okay, thank you.
The paper is open for questions, comments.
I have very short question. So I remember if I have a like Majorana zero, then the conductance is quantized. I know it's not like conclusive measure, but in your experiment, the conductance, is it similar to what's expected for the Majorana, or?
Yeah, that's a good question. So yes, in nanowire system, they measure the tunneling spectroscopy, and sometimes they measure the quantized states. But in STM measurement, it was very hard to get this region. So if you get closer and closer the tip tunnel junction to the sample, and eventually it will break the junctions. So we try to get into that region, but experimentally is not allowed. So we can get quantized.
So
yeah. Done. Sure.
So in this field, there are many questions about how to distinguish between accidental end mode and the really topological mode.
Yes.
So do you have any idea or remarks on that in that direction? No, how can experimentally, in your type of experiment, can you make sure that it's indeed not just an accidental end mode?
Okay, so that's always the criticism from the outside. So we always see zero end state in the case of my magnetic chain, and especially the spin polarization measurement. I think it tells you the difference between topologically trivial and non-trivial state. That's one part, and then the other part is in the second part. So hinge state, and I didn't talk about much about that system, but the magnetic moment of the cluster provides some special things. So when you measure the second system, sometimes we do see zero end state, and sometimes we do see very weak signals. And then we realize that depends on the magnetization of the magnetic clusters. And then I think this also tells you something about how the magnetization is really acting on this one-dimensional chain to develop this the bound states. So I think that can maybe tell you the difference between topological and non-topological systems. So, yes. And yes, it is quite confidence for me.
Actually, I have a question. So, for example, your niobium is probably type 2 superconductors, yes. And you have a one-dimensional ferromagnetic chain.
Yes.
In that case, you use the proximity effect between ferromagnetic chain and the niobium substrate. But I think if you have a 1D ferromagnetic kinds of superconductivity, something like superconductivity is different from the bulk niobium, something like that. Then, for example, we know if you have a 2D superconductor or 1D superconductor is very special. The fluctuating effect is very huge, so that the superconductivity is really different from the bulk superconductivity. But in your kinds of spectroscopy, looks like it's the same, and not much changes between the niobium itself and the ferromagnetic nanowire induced superconductivity. So,
okay.
Do you know? Can you explain why it's similar?
Yes.
Because it's ferromagnetic and 1D fluctuate a lot. Should be different. The superconducting parameters are different, but almost same. So I'm curious about that.
Yes. So I mean, this is just our observation, and our measurements. Is hard to tell what is really the origin of to get these results. But okay, so I'm going to divide into two parts. The first part is a magnetic chain. So on a lead substrate, very similar as niobium, but we do see Yeshiva region of states within the gap. So looks like the 1D magnetic chain is magnetic, but it's not strong enough to fully suppress the superconductivity on there. So it induces partially break the group of pairs nearby it, but it will not completely break the superconductivity. So that was the first part. And second part is why the superconductivity, proximitized superconductivity is really strong on this bismuth film. That was very, we don't understand at all, but somehow it's transparently proximitized to the through the edge state. That means it will not, I'm not sure this is a good way to explain it, but I think personally there's no strong way to break the superconductivity only along the edge states. Yeah, this is the only thing I can tell you.
Okay,
at the
or
moment.
your topological state protect
Yeah.
such kind of strong
Yeah.
effect.
It's not complete, but at least is very robust in our sense.
Thank you for your excellent work.
Thank you.